So we've got a circuit, the switch is initially open and the current is at 0. So for the time immediately after the switch is closed, answer the following. So what happens is we've got a current going through here. Right after the switch is closed, the inductor opposes current. So it's not going to be able to go through the wire with the inductor, and instead it's going to go through the wire with the 45 ohm resistor. And so we're trying to find the voltage across not 45 but 25 ohm resistor. So first of all, it tells us that, do we have 60 volts is, so I'll do part A here. 60 volts is our total voltage of the battery, and then the resistors are in series, so I'm just going to add resistor 1 and resistor 2 together, and so I get 60 over 30, which gives me a current of 2 amps. Part 2, and so that's not the final answer. I have to find the voltage through each resistor, or in particular the 25 ohm resistor, which means that I need to take the current that I just calculated times the resistance, and that gives me 50 volts. For part B, we want the rate of change of current in the inductor. So just when the switch is closed, we know that we just calculated that the voltage drop through this resistor is 50 volts, which means that the voltage drop through this inductor is going to be 50 volts, and therefore we have the voltage, which is the same as EMF, so I'm going to do it up here, is negative L di dt, and we've got 50 divided by the inductance, 0.1 is equal to di dt. If you simplify that out, that gives you 500 amps over seconds. Now the switch is closed for a long time. Determine the current in the inductor. So when the switch is closed for a long time, let me delete a bunch of this. We are going to treat the inductor as a wire, and that means that if I have no resistance here, I'm going to bypass the 25 ohm resistor right above it. So the current in the inductor is just going to be the full voltage of the battery divided by the resistor. Now that it's only going through one resistor, the 5 ohm resistor, which gives me 60 over 5, and that is 12 amps. All right, now here it says the energy stored in the inductor. So we're going to use the energy equation. I'm running out of room, so I'm going to go over here. This is for D. U is equal to 1/2 Li squared, and that gives me 1/2 0.1. I is equal to the 12 that I just calculated, and when you plug that in, you get 7.2 joules of energy. And then the next one says, after a long time, the switch is reopened. So when the switch is reopened, what ends up happening is that this is no longer a closed loop, but what we do have is, let me use the red highlighter, we have the inductor that has a current going in this direction, and it can create a closed loop through the 25 ohm resistor right here. So it's going to keep the current going to the right because it opposes change in current, but then it's going to go through this smaller loop rather than back to the battery where the switch is open. So we want the instantaneous voltage across the 25 ohm resistor. So to solve that, we start with the 25 volt battery has 12 amps of current going through it because the current doesn't change at the instant it's reopened. And then we've got the 25 ohm resistance. So that's V equals IR. And you end up with 300 volts going through the 25 ohm resistor, which is quite a bit more than what the battery provided. And then our graph, we graph voltage as a function of time across the 25 ohm resistor from the time when the switch is reopened. So we're going to start at our 300 volts, and because we lose energy as it goes through the resistor, we're going to decrease voltage in this fashion, which is directly proportional to the way the current decreases as the inductor discharges.